Well, if you've been working through all the videos for this week, I can say finally, we consider the ratio of two chi-squared variables, each divided by their own degrees of freedom. And again, a bit like where we derived the distribution of a chi-squared variable, derived the distribution of a t variable, might seem a bit weird as to why we might be interested in this. But let's go on our intrepid adventure anyway. So we've got the distributions of two independent chi-squareds with n and m degrees of freedom. They're independent, so the joint density is just the product of the two densities. Now my change of variables, again, I'm going to do this through a Jacobian, so I'm going to do the x equals s transformation, even though that's a little bit pointless. And the y is t over m divided by s over n. So it's the ratio of both of these divided by their own degrees of freedom. If I rearrange those, I get that s is x, I think that one's obvious, and t is m over n times xy. If we work out the Jacobian associated with those change of variables, the determinant of this Jacobian is mx over n. So if I take my joint density of s and t, and I replace s with x and t with mxy over n, remembering to multiply by the determinant of the Jacobian, mx over n, I've still got a bit of tidying up to do. If I start to do this, then it's not super straightforward. But what I want is I want the marginal density of y. I only really care about y, which was the ratio of one chi-squared divided by its own degrees of freedom to another chi-squared divided by its degrees of freedom. So if you notice, I've pulled every term out the front of the integral which depends, which is either a constant or depends only on y, and every term which still has an x in there I've left in the integral, and then I need to integrate out over the x. Again, I need a change of variable to do this. I was going to say neatly, but this is not particularly neat. As I say, please don't worry about this. If you want to do the integration practice, then you're a better mathematician than I am. But if you want to do the integration practice, just check any of this. But we will see that if we work through these integrals, then what we get to is we'll get to a gamma function at the back again, just as we did when we worked with deriving the density of a t distribution. So replacing that back term, the gamma function, I will get to this beautiful statement. Again, not easy en route, but I just want to justify where these have come from, because I think it's very easy when you first do a statistics subject where somebody says, you have this kind of data set, use a t distribution. You have this kind of data set, use a chi-squared. You have this kind of data set, use whatever. But without knowing where those come from. Because what I hope this set of videos for this week have shown is that all of these distributions are built on each other, and they're all built on two building blocks, which is the central limit theorem and the fact that squaring a standard normal gives a chi-squared variable. Everything's built up from there. And what that absolutely horrendous looking distribution was an F distribution, or a Fisher distribution, with m and n degrees of freedom. So there's 2 degrees of freedom in this, because it's the ratio of 2 chi-squareds, which potentially have different degrees of freedom. So that's Ronald Fisher, R.A. Fisher, who did a lot of work in sort of quantitative ecology and also, as you might suggest, in statistics, as you might expect. So again, it's a ratio of 2 chi-squareds, which are non-negative, so it has to be non-negative. Again, if I work out where the mode is, I can work out that as very large M and very large N, it begins to resemble a bell curve centered around 1. It's not going to be symmetric. It can't be symmetric, whereas a T distribution is symmetric. An F distribution can't be, because it can take values tending off towards positive infinity, but it can't go negative. So it's not ever going to be symmetrical, but it gets more and more symmetric for very large degrees of freedom. Okay, so we know that it's the ratio of a chi-squared divided by its own degrees of freedom to another chi-squared divided by its degrees of freedom. But why? Why did Fisher come up with this, and why does anybody care? Well, it's best known for its use in analysis of variance, or ANOVA. Because what you need for ANOVA is you compare the ratio of the variance between treatments to the variance within the same treatment. So what it is it's the ratio of 2 estimated variances. And if I'm estimating the variances based off a chi-squared distribution, which will be the correct distribution if I can safely assume the normality of residuals in the underlying linear model. So again, everything builds up, central limit theorem, squaring standard normals to get chi-squareds. All of these pieces build from the same assumptions. And as I say, I think it's very easy to do a statistics course where you're told this is the distribution to use, and then you're given this complicated density function and you've no idea where it's come from. But an F distribution is just an estimated is used to characterize an estimated variance divided by an estimated variance. So is the ratio of 2 chi-squareds suitably normalized. So that's why anybody cares about the F distribution. And you'll see that again later when we do a little bit of analysis of variance.